Okay, I guess we can begin. Is the microphone okay? Good. So we've made a lot of progress this year on many different fronts, and that's very satisfying. One thing, however, that has come up a little bit short is the question of models of type theory. What is a model of type theory? And what's really amazing is that we've been able to do so much without knowing the answer to that question. We can kind of reason semantically in type theory in a very natural way that seems perfectly sound without actually having a formal description of what such a model should be. And be that as it may, I don't know, you can draw whatever conclusion you like. Maybe we don't need any models of type theory. That might be the conclusion. We've come along perfectly fine writing the whole book without having to say what a model is. We just work in type theory, and that's the end of the story. Now, Mike Schulman called attention to the fact that it would be nice to have models of type theory, and in particular, to have a good description of what it means to interpret type theory into, say, an infinity topos, because that would be a useful kind of application. And he started the category theory semantics working group in an effort to get things going a little bit. And although we didn't come to any conclusion, one of the things that came out of that was an idea that maybe as a provisional interim step, we could try letting go of the idea of functorial semantics and just try to get something that works as a kind of first step. And then if we have something that works, then we can study that, analyze that, and maybe come up with a better tool to understand what the functorial semantics of homotopy type theory ought to be. And so I had an idea for doing that as a kind of preliminary step using pre-sheaf models. And so I rummaged around a little bit in my workshop, and I came up with a couple of different ingredients that are already there, and I cobbled them together in a certain way to give a kind of a first step toward finding some semantics for type theory. And the three ingredients that I'm putting together here, and then I gave it a bright, shiny name. I called it a natural model of type theory, but really maybe it's more like a Frankenstein model of type theory. But I think it's at least a step toward the sort of thing that we might be looking for in order to understand the semantics of type theory. So the three ingredients that I've patched together are, first of all, the observation that I made last semester that a representable map of presheaves, representable natural transformation, is really the same thing as a category with families. So this is a notion due to Grothendieck. This is a notion due to Peter de Bière, as far as I know. And these things are really the same. And I'll just recall briefly why that is the case. And then, so that's the first ingredient. The second ingredient is to ask, so this structure really gives an interpretation of types, terms, substitution, variables, and context extension, but no type theoretic operations. So the second step is to ask, when does such a gadget model the type theoretic constructors? So when does such a thing model, and in this talk I'm going to consider sigma, pi, and id, but of course one can do the other things. And it turns out that here we already have an answer almost suitable to this situation, and that's Vladimir's notion of a universe. So I'm going to use the notion of a Voevodsky universe, if I may, modified slightly in order to fit this particular situation. And I'll give you the modifications that I need and show you how that works. But I assume you're roughly familiar with how to model type theory using a universe. So once I make a universe, you know how it goes after that. And then the third step is to ask, well, this is a kind of pre-sheaf situation over an index category. when does the index category support such a structure? So I'll give you some axioms on such a gadget, which I call a natural model of type theory. And then I ask, when does the index category support or admit in a certain way such a natural model? And at that point, I need to use at least the ideas from a coherence theorem due to Peter Lumsdaine and Michael Warren. So I'm not going to actually apply that theorem, but I'm going to use some of the ideas that go into that theorem in order to build this model over the index category. So that's the third step, is when does a category C support, say, something of the kind 2. Okay, and then those are obviously the 3 parts of my talk. So let me start with a definition. I believe this is due to Grothendieck. Andre Joel will correct me if I'm wrong. So, a map of presheaves, so a natural transformation y to x. Presentable if, well, if its fibers are all representable maps. So for every, so I'm over some category C, presheaves on C. So if for every object C in C, and for every element, say, what do I want to call this? I guess I'll call this A in X at C. Let me start my diagram here. So here's my map. And now here's my object C. Here's the Oneida embedding, right? And here's my element A of X at C. So I don't have to remind you how the Oneida lemma works. So for every C and every A, there exists a, let's say, a D. And together with maps P from D down to C, so now I'm over here, together with a map Q, or an object Q, if you like, in Y at D, such that, so here's Q, isn't it? Because Q is in Y at D, Q, such that this square is a pullback. So this is simply saying that if I look at the map F and I look at its fiber over an element A in X at C, then that pre-image, that fiber, is itself a representable object with a map down to C. Good? Okay. And now, as I said, last semester I made the observation that a representable map of presheaves is really the same thing as a category with families in the sense of Debier. So a representable map, so presentable map equals category with families. And I'm not going to recall the whole definition of a category with families and then go through the proof that they're the same. There are notes from that lecture on the wiki, so you can just have a look. Instead, what I'll do is I'll start from such a thing, and I'll recover from it the structure of a category with families. And those of you who are familiar with that definition will then recognize that it is a category with families. And those of you who are not will thereby learn the definition of a category with families. So let's take some representable map. And now I'm going to already begin using some suggestive notation. I'm going to call this thing P, and it goes from U tilde to U. So over C. Of course, I'm thinking of this now as a kind of Voevodsky universe. And I'm going to define then And then I'm going to write the objects and arrows in C like this. I'm going to write them as though they were contexts. So I'll use Greek and I'll use gammas and deltas and so on. So think of the category C as a category of context and substitutions. Now what is U at gamma? Well, an object in U at gamma, so some A, say, I'll write that like this, gamma A type. So U is the presheaf of types in context gamma. And an object in U tilde of gamma, of course, I'm going to write gamma A is of type A. So U tilde is the presheaf of elements or of terms of type A. And then, of course, P is just the indexing projection of the term, right? So in particular, I have, again, using the Yoneda lemma, here is such an A. So here by Yoneda. And then if I have a term of type A, well, then that's just a lift like that into P. Okay? And now what is the naturality condition? Well, naturality just says if I take any substitution there, sigma, then I get a new term in the new context and a new type, sigma type, and a sigma, and then I have the functoriality conditions on these substitutions, sigma, if I take another one, tau, and so on. Okay, so there's the typing, the terms, and the substitutions are just built into the idea that this is a natural transformation of presheaves. What about the representability condition? So P is representable. What does that mean? Well, it means that if I take gamma, again, here's my A, here's U. And now, for any such A, I can make this pullback, and I get an object over on this side down in C. You see, I've dropped the little y for the Yoneda embedding because I'm using Greek over here. So you know when I'm in C and when I'm in presheaves. So this object, of course, I will call gamma.A, the context extension, and this will be the projection on the context extension. And so I have a sort of condition on this interpretation that says whenever I have gamma type A, then I get a context like this and a projection sigma or P, if you like, down to gamma. That's down in my index category, a map of contexts. And then, moreover, the fact that the diagram is a pullback says that whenever I have any, let's just do it quickly here. Whenever I have any sigma and an element, what should this thing be called? T? Yeah. Whenever I have in context gamma like this some sigma, and so given this and given a term in context delta, so this is T, it has type A sigma, then there must be sigma T. And now what type, gosh, does that thing have? Oh, that's not a type, that's a transformation, or rather a substitution from here into here. Such that, and then you can write down the equations, right? Such that P A after sigma tau is sigma q a, that's this map here, q. Did I put that in there? Yeah, I need to have this thing right here. So that's q. So I get this, I get this, and I get this, of course. That's a term. Q is a term in type gamma a sigma a. So that's QA is a term in type sigma a. Okay? And then Q P. PA, yeah. PA. Good? Yep. QA is in type APA. And QA then composed with sigma tau acts like the second projection. And then there's another, there are two more laws. One is the identity and one is the naturality. So if you're familiar with the definition of a category of families, you'll recognize this as exactly the rules for context extension. So these are the rules for context extension in the definition of a category of families. And they say, so summarizing, what they say is exactly that this natural transformation is representable. So, okay. So that is, I think, the end of part one. No, I have to put that in if I want a terminal object. If you want that to be part of the definition of a category of families, you put it in. So you can think of a kind of, you can think of a representable natural transformation as classifying a family or a class of maps in C, namely all of its pullbacks, which themselves are stable under pullback. So if I take a family of maps in C, stable under pullback, that determines, in a way that I'll show you later, such a representable transformation. Okay, so two. Given such a thing, so now I'm given such a representable natural transformation, when does it model the rules of type theory? Well, it models the structural rules. We just saw that. So the rules of, say, sigma pi and identity types. And again, as I said before, I'm thinking of this now as a Voevodsky universe in the presheaves. And so we, roughly speaking, know what structure has to be present on that universe in order to model type theory internally in the presheaves. And I'm going to kind of unwind and modify a little bit that idea coming from Vladimir's simplicial model. So first of all, I need the following fact. Let's consider the polynomial functor associated with this map P. So it looks like this. I'm going to write capital P. It's really capital P of little p. And if I apply it to an arbitrary object x, I get something that I'll write like this. This is the indexing over the universe. And then the fiber over the universe of A, I'm just going to write as A again. So then I take x and I exponentiate it by A, where I'm writing A here also for, if you like, P inverse of A. It's a little bit funny, but I think you get the idea. This is the standard notation for polynomial functors, right? And it corresponds to the idea that these things are both names of types when I map into the universe, and they are types themselves when I pull back. So I could write here gamma dot A, right, as the context extension to indicate the pullback. But this is the usual notation. And now I want to consider maps into this object in general. So this thing px classifies things of this form. I take a map gamma into p of x, so let me write it like that. A, u, x, a. Now, one thing I can do is I can compose with the projection down to u, pull back, and I get my context extension here, gamma a. But then, with a little more fiddling around with this polynomial functor, you see that what you also get is a map like this into x itself. So what I claim, and I'll leave this as an exercise, or I'll give you a proof later on after the talk, is that maps gamma into sigma, and now let me apply the polynomial functor to itself. So in place of x, I put here u to the a, correspond to things like this. I have gamma, and then I have a context extension of gamma. So that is a map from gamma into u, pulled back to give a context extension. And then I have a map like this into u again. So if I think of this thing as a, right, down here, and here's the type it classifies, then here's a type b in context a. So these things I'll write like this. It's an extended context a and a type b in context gamma extended by a. Okay, so if this seems a little mysterious, think of it like this. This thing, if you think of it in terms of its generalized elements, u to the a, has as a generalized element, so the generalized elements of this have the form, right, for any gamma mapping in, well, it's an a of type u together with a b of type a arrows u. And that's exactly what I've written here. Good? All right. So let's do the following. I'm going to take now p of u, give myself a little more room, p of u. So again, that's sigma a in u to the a. And I'm going to consider a diagram of this form. Where now I applied the polynomial functor p to u tilde. And of course here I apply it to p, little p. This is p applied to little p. And so now suppose we have a diagram of this form. What is this thing doing, or what is such a thing saying? So this, I assume, exists, right? This one is just the polynomial functor p applied to that p. And now I'm going to label this suggestively pi, and this one lambda. And what is this doing? This is taking an extended context with b over to something of the form, or here, let me drop the gamma because everything is parametric in gamma now. Pi a b. This thing, if you analyze it, is taking terms of this sort, a b of type b. This is just the indexing projection for the term over to a term here, lambda b. Lambda b. And the typing of lambda b, because I'm requiring the diagram to commute, is just lambda b of type gamma ab. So a structure of the form big P and big pi and lambda is a pair of arrows like this making this square commute. And now if I require this square to be a pullback, what does that tell me? So pullback says it says that for every AB and for every f of type pi AB, right? Because after all, the f has to go down and have this type, pi AB. There exists a unique thing back here, so that's some A B of type B, such that when I apply lambda to B, I get F. So that's exactly the usual rule there for the lambda and the pi operations. So this is my condition then. So here's the fact, if you like, is that P models pi types is equivalent to there are maps pi and lambda as above, such that this square here is a pullback. So that's our condition on U. And let me just say once again, I'm using Vladimir's idea of modeling pi types in a universe, except I've made a kind of modification here in that I actually define, rather than saying take the generic two-step extension and apply the pi functor in presheaves and then require that that is classified by this, which would be a kind of, well, thinking of this as a, what's it called again? Logical framework. That would be what Bob Harper called the analytic representation. I'm using the synthetic representation, I think, I'm not sure if I have the terms right, which says actually specify this type as the type of terms like this, and then just require this diagram to be a pullback. So I'm not making reference to the ambient structure, pi structure on the presheaves. Okay? And that, I think, has some advantages when it comes to considering what the morphisms of these things should be, but I won't be able to get to that today. Okay, let's do something similar now for the sigma. So for sigma, I'm going to start with, of course, the polynomial functor here. Again, because that classifies things of the right shape for the type constructor, that is the premise of the formation rule for sigma types. That has things that look like this, A, B. And then I'm going to ask for a map into U. But this will be, of course, a different map. Allow me to write sigma again for the same map. Don't confuse these two things. So that will be sigma A, B. That's the idea there. And now the trick is to discover what goes here, right? Well, we know what it should look like. It should be a type which classifies things of the following form. A is a type. B is a map from A into U. And then A is a term of type A, and B is a term of type, so now we can apply this, B of A. So it should classify things like that. And if you work it out, or if you look it up, and I'll tell you in a minute where you can look up such a thing, which is what I finally had to do after struggling with it for a while, you see that what this is it's a sigma over these things, so a sigma over all things of this form. So let me just write pairs AB in P of U. And then, so that gives me these things to work with now. And then I take sigma x in A, B of x. Okay? Okay, so that's my signature for things like this. Okay, and then, of course, I take this over to here with an operation which I call pairing. And that tells me that if I take such a gadget like this, I bring it over here, I get a pair AB, which has this type. Sigma A, B. And now here's an interesting fact that Andre Joyal suggested to me last night. Every map in a Cartesian closed category like presheaves represents a polynomial functor, right? So here I've taken the polynomial functor, I'm calling it big P, to be the one represented by little p. This construction is known in the theory of polynomial functors. It's the map that represents the composite of p with itself. So this thing could be called p squared, or p composed with p. Well, really it's big P of little p composed with big P of little p, and it's the thing that represents that. Oh, it's quite interesting, right? And also, there's a notion of map of polynomial functors, and a map of polynomial functors is a commutative square between the representing maps, which is a pullback. So, of course, it's interesting to consider when that is a pullback, because that says we have a map from p squared to p. This is starting to look kind of operatic. So, oh, and by the way, that's how you can look up what this thing ought to be, is by looking for composition of polynomial functors, and then you discover what this thing is. So what does it mean to have this square again to be a pullback? Well, I guess maybe I won't go through it. I think you can see how it works. It says for any pair here, right, anything like this, oh, sorry, for any term up here, right, if it has this type, then there exists a pair of things like this which pair up to that term and have this type. So the pullback condition is equivalent to, did I write? So here's my fact again. Maybe I'll write it here. Fact is this is a pullback is equivalent to P models strong sigma types. All right. Okay, so that's, I think, all I have to say about that. So finally, the identity types. Now that's a little more tricky. Just see if I'm leaving anything out. I think I have to roll up my sleeves for the identity types.
So if you want to model, so this is sort of extensional, right? Because
Well, it's not extensional, I beg your pardon, but it is strong sums in the sense that we have surjective pairing.
okay.
Extensional means different things to different people,
Yeah.
but I don't want it to mean this, because I'm going to use it in a minute to mean something else. Okay, so no, I mean, there's another way of getting the weak inductive sums, and I think you'll see how to do it after I do the identity types. Then you'll see the trick that is used to make things weak, and you could apply that trick here if you want weak sums. Okay, so for the introduction rule, so let's look at the identity types. So the introduction rule wants to look like this. If we have some, we have gamma and we have A is a type, and then we have, let me do it like this. We have id, we have A of type A and A prime of type A, then we get id, A prime is a type, and then we have our, so that's the formation, and then we have the introduction rule looks like this. For any A of type A, we get a term RA. I don't need that. Id A, A. So that's what I'm trying to capture. And let me just cut right to the chase. I'll take U here. I'll take U tilde P here. Like this, and I take the pullback of P against itself. So that's U tilde, U tilde. And then I take the diagonal map given by the identity here. And I consider the following So, and I consider, I'll do it here. And I consider P into U. And now, kind of following the pattern of the other constructors that we had, I consider a situation where I ask for structure like this, making that commute. So here, P model strong sigma types. This is a pullback. So, right, what I need is P together with the specified structure maps, which were sigma and this pairing, right? So here, too, I have this, I guess I formulated this in a slightly different form, but the idea is you have this specified structure. So for identity types, let's consider a structure like this, right? So what is this doing? It's saying, given a pair A and A prime of elements, both of the same type A, this thing returns a type, which I'll write I, A prime, and given a single element A, again, of type A, this thing returns an I of A, which has this type. So A, but it has this type after you go around, so it came through the diagonal. Good, so a structure like this gives me type-forming operation and a term-forming operation, and so it models that introduction rule. Now, what about modeling elimination? Well, in the other cases, what we did was we took a pullback here. So that's the first thing to try and see if we get lucky. Let's see what happens if we ask this thing to be a pullback. So 3 stars is a pullback. What does that say? Let's go through it. It says that for any A and A prime in A, and any term of this type, so that's some P, say, of type I, A prime, there exists uniquely an A in A such that A, the pair, so I've gone to the diagonal now, A prime is equal, AA is equal to A prime, and therefore A is equal to A prime. And P is the reflexivity term there on A. So we have exactly the rules for extensional identity types, exactly the elimination rule for extensional identity types. So that is for extensional identity rules. So that's why I want to be careful about the use of extensional, because that's what I want extensional to mean. Okay, so to get the intentional identity elimination rule, we're going to have to be more tricky. And there is a, so the introduction form, again, agrees with Vladimir's, which is, I think, in the paper of, so here, there's a, the paper is Kapulkin, Lumsdain, and Voevodsky, and I guess only, yeah, some of them are here at least. And, but then they, in this particular connection, they cite Michael Warren as having given the elimination, or the introduction elimination rule. And I'm going to, again, modify the elimination part in order to get something that I think is at least more suitable for my purposes. So we start with that diagram, and I'm going to spread it out a little bit, because I'm not going to assume that this thing is a pullback, because I don't want to have extensional identity types. And so I'm going to have the correct introduction rule here. P. So there's I. But now I'm going to make, because this is not a pullback, I can make the pullback. And I'm going to call this object, well, I'd like to call it I. I'll call it id for the identity type. It's a kind of generic identity type. And of course, because it commutes, there's a factorization here, and I'm going to call that R. You were wondering why I didn't use R for little I, and this is why, because that's R. It's, of course, completely determined by I, so these things are interchangeable, but that's the structure that I'm going to be interested in now, and now I need to have a condition on this thing. So I need a condition, a further condition on the pair I, well, let me say little I, or I and R, other than pullback. That was too strong. And the condition, morally speaking, is that this map R has the left lifting property with respect to this map P. And why do I say morally speaking? Because it's not enough to require in that one instance that R and P have the left lifting property with respect to each other. Because of the naturality condition, so this is now for the insiders, because of the naturality condition on the J terms and the elimination from Martin-Left type theory, you require not only that the J's, that is the diagonal lifts, exist, but they have to exist in a coherent way. And in order to get that to happen, you need to use another tricky idea for this to do this. And what I'm going to do is sketch it for you. I'm not going to give you the whole details of the proof of naturality and so on, because that would require me to define the naturality that I'm interested in, which is a little bit too technical for this situation. But let me say I'm going to define this new notion, which is a kind of strong or internal left lifting property. And that will be then the condition that I apply to R and to P to give the correct form of the elimination rule. So let's step back for a minute and look at the following situation. Suppose I have maps. Let's see, how do I want to do this index? I always get mixed up with this indexing, but you're probably going to have to help me out here. I'm going to take A and B here, F, and I'm going to take C and D here, G. And I want to say that these things stand in, have the left lifting property, but they have it in this strong internal sense. So how do I say such a thing? Well, what I want to say, of course, is given any commutative square like this, there exists a diagonal filler, but I want to say it internally. So let's consider instead, so let's make instead the following diagram. We'll take A, B, and we'll raise it to the power of, and now which one should I do first to get this to be going this way? This is going to be contravariant, so it's going to go back like that. So I guess I should put the C here. I raise this to the power of C, and then I do the same thing over here, raising it to the power of D. Here is F to the D. And now there are maps here and here, I hope. This should be A to the power of G. So this is pre-composition with G. Got it. A to the power of G. And this is B to the power of G. And so what is the commutativity of this square telling me? It's saying if I start with a map from D to A, it's a diagonal map like this, right? And I pre-compose with G to get over here. So let's, well, to get over to here, pre-compose with G, and then I post-compose with F, pre-compose with G. Ugh, what am I doing?
Down, across, and down again. C to D, D to A, A to C.
Have I got it wrong?
That's fine.
Okay, good. So what this tells me is that if I start with a map, if I start with something in here, that's a diagonal, and I pre-compose with G, and I post-compose with F, that's the same as taking this and post-composing with F and then pre-composing with G, right? So that's what the commutativity of this square is telling me. And the diagonal filling property that I'm interested in says, if I start with something here from B to D, it's like this, and something here from C to A, like this, such that they agree when I get down to here, which says that the square commutes, then, well, there exists something back here that is a diagonal filler such that when I apply those operations that I just mentioned, the result is precomposing with G is this one, and postcomposing with F is this one. Now, notice what I said was there exists something back here that hits this one and hits this one. I didn't say there exists a unique one. Orthogonal factorization in the strict sense would say that this diagram is a pullback, right? That for every such square there exists a unique filler. However, what I want is not that there's a unique filler, but rather there exists one. So sometimes this is called being a quasi-pullback, but I want an even stronger property than quasi-pullback. I want there to be an explicit section, a choice of those things. So what I'm going to do instead is I take the pullback here. There's a canonical map right there, is a comparison map, and I put in a section for that map. And that section that I put in is J. So my condition is when I take, so I'll say that G has the internal or strong left lifting property with respect to F. That means that the canonical comparison map A to the D into this pullback B to the D cross A to the C over B to the C has a selected section J. So I really should put that in there. Okay, so that's my condition, and now I apply that condition right here. So I want R and L to have that strong left lifting property with respect to an explicit section J. And that, if you untangle it, is the elimination rule for the Martin-Leff identity type.
It might be worth mentioning that this map in the pullback is familiar from polynomial factories, since it's what would be a trivial fibration in polynomial factories.
Good. I don't need to mention it because you just did. Yep. So my fact now in kind of in parallel formulation to these other things is that P, together with the structure I, and J, models the identity.
So you don't ever, here in this place, you don't have to use the locally Cartesian closed structure. You only use Cartesian closed.
Well, the argument that I actually give to show that this holds uses the locally Cartesian closed structure, because I have to do all of these pullbacks over. I have to map into U and verify that this holds locally over any type that I've built by mapping into U, right? And for that, I have to pull this. I have to pull this thing back.
But all these exponentiations are absolute exponentiations, or are they relative exponentiations?
They are exponentiations
Over
over U.
U.
Okay.
And that
Yeah.
sort of makes.
I have to make the whole thing over U.
That makes. This is why this is your argument, right?
Yep.
Exponentiation. I mean,
So in that case, it's a to the power d over.
So I replace this by R, and I replace this by, over U, over U, and I replace this by P as a constant map over U. So I pull P back up over U, and now I have two maps over U, and I build this condition over U.
Okay, then it should be similar to what, you're right.
but that's on the face of it, it's exponentiations in pre-sheaves.
Yeah, it's just exponentiation in pre-sheaves, because slicing over U is another pre-sheaf category.
You can express the conditions anyway.
Oh, sure.
Because there is exponentiation in pre-sheaves.
Yeah, so that would be the fourth part of this talk, is to unwind everything explicitly into pre-sheaves and give a kind of Kripke-Joyal semantics, right? Because after all, this is just pre-sheaves, so we should be able to unwind everything and just state it in terms of, well, pre-sheaves in a kind of.
But that applies more generally in any LCC.
This condition can be formulated in any LCCC. Yeah, yeah.
You mean that this theory could be formulated in any LC?
This notion, which I'm going to define right now, so this notion, which I'm going to define right now, makes sense in any LCCC. So let me define might as well glorify this with a name. Yep.
Are you sure that you have to do it over U? You may have to do it over U tilde, no?
I think I can do it over, I think I do it over U.
Do you think to do it on U or U tilde corresponds to, I think, the equivalence of the Palin-Moring identity type
Oh.
rule, one-sided one, and
That would be interesting.
and both the version where just the type is a parameter, or where a type and a term are both parameters. So I was doing following Morin.
Oh, okay.
I did it over U tilde, and you
Oh,
were
good.
doing
Okay.
classical
Good.
one, so you
Good.
did it over this.
Theory is or consists of, so over a category C consists of, and now I'm just going to assemble all this stuff. So representable map of pre-sheaves, and then structure maps as indicated before, pi, lambda, sigma, pairing, I, and j. Satisfying those conditions. And now the theorem then, if you like, but it's really just unwinding Vladimir's idea there, is that any natural model regarded as a category with families, if you like to think of it that way, families, models, the type theory with sigma, pi, and it. So now the question is, where can you define this notion? And the answer is you can define it in any locally Cartesian closed category. So this notion can be defined there. But not, so I've done it in pre-sheaves in particular, right? But you could do it in a locally Cartesian closed category. You'd have to then say, well, then you're back in Vladimir's situation. Here, I've used the fact that we're in pre-sheaves to talk about a representable map, and that takes care of the context extensions. If you were doing it in an arbitrary LCC, you'd have to start with a terminal object, make the pullback for the basic types, and then iterate the pullback structure to do the way Vladimir does to get a contextual category. Yeah? But here's the point, though. I like to do it in pre-sheaves over C for a particular reason. Because now what we can do is we can say, this condition of this thing being representable, together with this having a certain algebraic structure on it, imposes a condition on C. Yeah? Because the representability pushes some of this structure back down to C. And now I can ask, when does a category C support such a model? And I think of this now as not a model in pre-sheaves on C. I think of this as a model in C, or over C, if you like. So the idea is that this thing is a way of modeling type theory over C. Yeah? It's an algebraic gadget on C, and that's the model of type theory. And now, familiarly, there's a problem about interpreting type theory into a category because of the mismatch between the strictness of type theory and the up to isomorphism looseness of a category. And that mismatch now I want to solve in the way I set up this map here. I'm going to build that into this interpretation so that we can interpret type theory using the notion of a natural model over very general categories. We don't have to require strictness or coherence conditions on the category C. And that's where I'm going to use the ideas of Peter and Michael. So let me just sketch how that goes. This is 3. So again, the question is, what is required of C to, let me say, support such a natural model? And I think it'll be clear what I mean by support when I do the construction. Okay? So I need to make, first of all, P U tilde to U. And remember I said before that such a representable map of presheaves corresponds to a pullback stable class of maps on the index category C. Okay? So suppose we have, and first of all, let's not suppose that it's pullback stable. Let's just suppose we have some class R. I'm thinking of these as right maps in the arrows of C. And I'm going to write these like this, and then we'll see what we have to require of them. And then we'll define. I'm going to define now two presheaves and a map between them. So U is going to be at, so again I'm going to write the objects of my category. Right. This is how I'm writing my category. C is going to be the set of all things of this form. I take a map like this, and then a right map like that. And U tilde is going to be the set of all maps of this form with a right map here. Yeah, gamma, thank you. That's where the gamma comes in. So U is the set of all maps out of gamma into the base of a right map. U tilde is the maps out of gamma into the top of a right map. And then, of course, the map from here to here, P at gamma, is just the composition map. I take one of these guys, I compose it like that, and I get one of these guys. So why is that natural? Well, it's obviously natural, isn't it? Because if I have something like this, and then I compose it through to get something like that, if I precompose with some sigma, then the action is just going to be precomposition like that. And then I compose it through, and I get something like that. So that operation P gamma commutes with precomposition. I could write it like this. So the map from here to here this is, what is this? This is U at sigma. This is U tilde at sigma. This is P at gamma. This obviously commutes. This is P at delta. Obviously commutes because it's just precomposition and then postcomposition. Right? Okay, so that's my map of presheaves, which is going to be my universe. Let's look at, Yoneda helps us again in order to understand when that thing is representable. So we want P so defined, this particular P, to be representable. So Yoneda tells us that we have here u tilde p u. And now here's gamma. And here's some, I didn't give these any names, did I? So let me just have some names for these. If this thing, so an element of this thing, A, right? I guess we were writing these before like this, gamma A type, right? So if this is an A, is an element of this, then the corresponding element like this, I'm going to write like this. I'll call this thing A naught. I'll call this A1. If I need to mention this, I'll call this P sub A. And if I need to mention this, I'll call this absolute values of A. It's a whole structure corresponding to this A, right? And similarly, up here, the elements gamma, A, well, this will just be little a there. Okay? So an A here corresponds to something like that. And in fact, what you can do is you can show quite easily that I can interpolate here A naught. Of course, I'm just applying Yoneda now to that element. So here's this A here. Here is A1. And now this thing here, together with the identity map on the base, gives me an element of U over A naught, right? Which I can put in right there. And here I can show that that's a pullback. So this is the situation that I have that's just given by the definition of P as I've specified it. And now for this to be representable, I require that for any A, P pulls back. So I have to have some gamma A back here. Well, of course, because this is a pullback, I'll have another pullback here. So here I'll have a representable, here I'll have a map as well, which will be a pullback of this one. So this was a right map, right? So what I will require then is that the class of right maps be stable under pullback. So if R is stable under pullback, then P, as defined above, is representable. So that's my first condition, right? I'm going to kind of go through, but I'm not going to go through it step by step, and ask what conditions are required on C by that definition of a natural model. And the first condition is that I have a class of maps which are stable under pullback. And that gives me a representable map of free sheaves. So doing okay for time. This is good. Maybe I'll just maybe I'll just state the conditions that I need here. So let me say so it should be no surprise that I'm going to need some kind of pi functors in order to interpret the pi's, and I'm going to need a weak factorization system in order to interpret the identity types. So that's what it turns out to be. But let me just capture that, the specific form that I need as follows. Let's C have a weak factorization system, LR, such that, first of all, I want the right maps in the weak factorization system to all have pullbacks along any map, or putting it the other way around, the right maps to allow pullback of any map along them. So for any right map, F from B to A, and any map A prime to A, there's a pullback square. I guess we'll look at it. I'm looking at it this way, I guess. A prime to A. B is a pullback square, and it follows then, because it's a weak factorization system, that this map on the left is also a right map. So now because of that, I have pullback functors along right maps. So we have pullback along right maps. So whenever I have B a right map, F to A, there's an induced pullback functor now going this way, C, for the whole category. But if I just look at the right maps over A, the full subcategory of right maps over A, then this restricts right by the observation that I just made that this thing here is again a right map because of the weak factorization system. And now what I want is that when I consider this functor, that one has a right adjoint. So that is to say, so we have pullbacks along any right maps, then the right adjoint along any right map exists. The right adjoint, I still have to be more careful here, sorry. It's a little bit fussy, but it's not a complicated idea, you just have to say it right. I'll try it like this. The pullback along any right map restricted to right maps has a right adjoint. Right adjoint, which furthermore preserves right maps. Which preserves right maps. That's quite a mouthful, but I think that's the right way to say it, right? If I have a right map here, I can make a pullback functor for the whole slice category, right? Now, I don't want to require that thing to have a right adjoint, but if I restrict it down to just the right maps, then I can have a pullback functor just on the right maps because that pullback functor preserves right maps. And now that functor is required to have a right adjoint. And moreover, because it's restricted down here, the right adjoint, which you might think goes up to here, lands back in R. So it has, again, the property of preserving right maps. If it's a right adjoint defined globally, it automatically does it. But the way I've said it, maybe it's an awkward way, is I'm only looking at this pullback functor restricted to right adjoints. So, is it okay? It automatically preserves.
No, but what I mean is that
I would need the pullback to preserve the left maps. Don't I need pullback to preserve left maps if I want that?
Product to be a product with respect to everything, not
Yeah.
with respect to
Yeah.
the right map. And in this case, it would be.
Yeah, but I just said that purely formally, the requirement is that the functor between the categories of right maps has a right.
Oh, yeah, sure. Yeah, yeah. Yeah, okay,
That
okay.
contains.
Yeah, okay, well. Yeah, just the way I've written it here. Yeah, sure. Okay.
Is
Okay.
it not equivalent to asking that each category array is category code?
Maybe, that may be the case. Yeah, that could be the case. Anyway, so,
There is one,
Yep.
there is one slight, slight suspicious place here, and
Mm.
this is you really have to require, in order for the construction of U to work, you really need a set of right maps.
okay, very good. So I need either C to be small.
Either C
Or
or
something.
small or something like that.
Very good. Yep, thanks. This condition, because it's kind of a mouthful, I have to give a name. I'm going to call this having right pies. Right, because it has all these right things in it. Right maps, right adjoint. So that's a condition of right pies. So now the theorem is that if C factorization system with right pies then this particular P that I defined back here, right, which I said in the very beginning, but Peter wasn't here, so I'll say it again, builds in the idea of Lumsdaine and Warren for making a coherent or strictification of a pullback functor. Then this particular P is a natural model. So I'm not going to be able to prove that, but I can give you a kind of a sketch of the, some of the important ingredients. But before I do, I want to make a couple of remarks about what's going on here. So I guess the first thing I want to mention is that the idea behind this interpretation, which, as I said, kind of builds in a coherence property, is that we can model type theory now strictly, not just up to something, but a real strict model in an underlying category which doesn't need to be assumed to have some canonical choices of this or that, right? It doesn't have to be a natural weak factorization system or a cloven weak factorization system. It doesn't have to have more path objects. It doesn't have to have any of these devices that in the past we've built into the category itself in order to strictify it sufficiently to get a model of the strict type theory. Instead, we take the category as it is, and then we build the strictification, if you like, into the definition of the structure that's varying over it. And I think that works out much more nicely. So,
With respect to which quality you have coherence? Because coherence depends on the quality of your installation.
the equality is the identity on the category of objects and arrows, on the index category, together with the identity among sets, which are the values of the presheaves, and those two things together determine the identity among the presheaves and the arrows between the presheaves, the natural transformations. So
It has
it's
nothing to do with, for example, this just basically this more or less extension equalities in sets.
well, I'm not sure. I mean, it uses the equality of functions in sets to define the equality of natural transformations, which in our interpretation is the definitional notion of equality, is equality of natural transformations. I mean, it's not the identity type. The identity type is an internal construction to the model. U, yeah,
U of gamma and a set. I mean, consider different ace of zeros.
yeah,
Right? So to ask whether different elements of the set U of gamma are equal, you have to ask whether those ace of zeros are equal in
yeah,
the sets.
yeah. So it uses the identity on the category and even on the objects, even on the objects in the category.
It requires
Let me go back here and let me go back here and say small just to take account of Vladimir's. If I was going to do this over groupoids or simplicial sets or something like that, I would have to take a small subcategory, take a universe in there or something like that. It's obvious that I need some kind of pi-like condition to get the pi in the interpretation. What's not obvious, although I think I won't have time to show you, is that I actually need the pi condition in order to verify the identity type elimination rule. So that pi condition really seems to be essential just to even get the identity types to work out right. And that's an observation that I think Peter and Michael had as well in their strictification theorem, which is not yet written. What else? Oh, on the other hand, this device of strictifying by using these squares like this or these corners like this, I think is not just a hack at all. It seems to be quite natural, if you'll pardon the pun. When you go through these constructions and start getting used to working with these things, these are the kinds of things that come up when you're considering a weak factorization system on a category, right? So in looking at the way that this model works over a category, index category with a weak factorization system, this kind of structure being a dependent type is actually playing some role. It's doing some work in this construction. It's not just a device to get this thing to actually be a strict presheet. So I guess maybe that's all I had to say. So let's look at, I have a couple of minutes. Maybe you'd like to see how the identity type comes about in this model. So I can do maybe I do the identity elimination rule, or the identity introduction rule. Oh, well, there it is right there. So this is what I need. And we know what this thing is now. I've given a definition of that. So I'm going to start by taking an arbitrary so take any A1, take any right map like this and factor its diagonal. Factor. So what I mean by that is make for A naught this pullback, A1, and then I get the diagonal map here. There's the delta, and then I take that delta, A1, into, so there's delta, and I pick a factorization, which I'll call IA. And because I'm in a weak factorization system, there always is such a one, and because by exists, I mean the constructive notion of exists, there is a selected one. So this is my map RA. And now I'll take, let me do this over here. So make, so I take U tilde. At the same time, I make this thing here u tilde with its diagonal, so etc. And then I get here u and a factorization of this diagonal. So what I'm looking for is this object I. So this is delta. Okay, so I want I. So let's hum into that picture there and see what we get and see if we can fill in something in between.
Are you trying to, at the moment, to construct I?
Yes.
Yes, that's what you.
Yeah. I'm defining I in terms of a weak factorization system on the index category.
Yeah. So you want the natural transformation I from U to the.
No, first I want to have a presheaf I. I have to define this presheaf I. I have defined U and U tilde and P, and from that I get the rest of this structure. I have this structure P.
We have a representable.
Map of I have a particular one, which I've already defined. I have a particular P, which is that one over there. My index category is has a weak factorization system, and I want to use that weak factorization system to define a presheaf I, which factors the diagonal.
And then you'll need to classify the map from I to U tilde times U tilde.
Yep. I need to make a presheaf I equipped with these two maps.
Yeah, no, but you'll need to make sure that this presheaf I, that its projection, that its map to U tilde
Yeah, yeah.
times U tilde is classifiable from P.
Yep. Yep.
To start with, you need a little more than
I need a little more I, more than I.
more than just the presheaf. You need.
Yeah, well, let me do it, and then we'll see, okay? So I'm going to take what is gamma, what is U at gamma, let's recall. Maybe I'll do it this way. I'll take U. No. U at gamma was maps like this, gamma A and U tilde at gamma is maps like this. So what is U tilde cross U at gamma? Well, that's pairs of maps like this, right? A prime, A1, A naught over A. And so that's the same thing as maps from gamma into A1 cross A1. Okay, so that's my pairs. And now what I'm going to do is I have A1, A prime. I have already selected a factorization like this for this map A, right? And so for I at gamma, I will simply take maps here, let me say Q, into that factorization AI. Okay? Because this structure is given, right, by the factorization that I've already selected for A. So really, what I'm doing here is I'm saying once and for all over U, make a generic factorization of the diagonal I U tilde. That's what I'm trying to do. And the way I do it is for any gamma and A, well, here I know I have, let me do it differently here. This A looks like this, but I can factor it through my, I can factor it through A naught like this. Do I want to do that? No, I'm not going to do that. Sorry. Yes, I am going to. There we go. So there's A1. So I have my pullback here. And now I made, once and for all, a choice of a factorization right here. A. This is delta at A. And I know that these things are all pullbacks. And now I've defined A by representing maps from gamma into here. So this thing is just maps from gamma into here. And then I take those maps up to here of that form, which compose through to give me the chosen pair. Okay, so that's a kind of sketch. This object here of maps of this form obviously maps down to this one, right? Just by composing with the Q to get a pair like this. Good?
If I may, observation.
Yeah. So maybe one.
The reason, one reason this is possible is the fact that U is the product of representable, as well as U tilde, as well as U tilde cross U tilde over U.
Mm-hmm.
All your presheaves are coproduct of representable. They are free.
Mm-hmm.
They are free presheaves. They are all.
Mm-hmm.
And therefore, it's very easy to define maps between them.
Okay.
You just have to specify
What they do on the representables?
generators by unit of
Uh-huh.
and that works.
Mm-hmm. Okay, very good. So they're familially representable coproducts.
I'm sorry?
Familially representable presheaves, I think. I think they're called that by Peter Johnstone, coproducts of representables, called
Coproduct of representable.
familially representable, I believe, yeah.
They are soft with
Free presheaves.
Like,
Okay?
and so it's very easy to define maps.
Yeah, it is.
Information between them.
Mhm.
And you're specifying it on the generators.
On the generator, and then it works. Good. Okay, that seems right to me. I think that's enough. Okay, thanks.